Number 4 says a researcher conducted a medical study to investigate whether taking a low-dose aspirin reduces the chance of developing colon cancer. 100 adult volunteers were randomly assigned to one of two groups. Half of the volunteers were assigned to an experimental group and took a low-dose aspirin, and the other half were assigned to a control group and took a placebo. At the end of 6 weeks, 15 of the people who took the low-dose aspirin developed cancer. 26 of the people who took the placebo had developed colon cancer. At the significance... Oh, we're doing a hypothesis test. So I'm going to start by writing the null and alternative. All right. Do the data provide convincing statistical evidence that taking a low-dose aspirin each day would reduce the chance of developing colon cancer? All right. So I need some parameters to write about. Is this going to be a P or a mu scenario? Am I measuring something or am I counting something? All right, I am counting something, so it's going to be P. And so I need to have, in this case I have two groups, so I have two different P's. So I'm going to have P with low-dose aspirin, so we'll say PA, is equal to P placebo. So I'm going to go placebo. That's a PL. So aspirin equals placebo. And remember, when we're doing it like this, I'm going to go P aspirin minus P placebo equals 0. Let's move it over. And then I'm testing to see if P aspirin does taking a low-dose aspirin each day reduce? So I want to find out, is this less than P placebo? All right, so I got my hypotheses written. Oh, I'm going to rewrite it. PA minus PPL less than 0. All right, I've got my hypotheses written, and now I need to verify my conditions. So I stated it, and now I'm going to do my plan. Stated random assignment into two groups. Okay. If you would have said simple random sample, you would not get credit for that. All right. So I'm going to, let's see, so that's random. Independence. There are over 1,000 times 10 equals 10,000 adults to choose from. Therefore, independent. Then, since it's a proportion problem, I'm counting number of successes, and success count are both over 10. NP and NQ, that is. Remember, NP greater than 10, NQ greater than 10. So in this case, both success counts are over 10 and failures over 10. Which means, let's see. Oh, sigma is known. That's back up here. Sigma sub p hat is known. So, what's an S? Use to proportion. Z test. There are two proportions. It's Z because I know sigma. I forgot to say up here, therefore, sampling distribution is approximately normal. All right, those are my conditions, SINS verified. I can move on and think about my formula. My test statistic is Z equals statistic minus parameter. So P hat 1, or P hat A, minus P hat PL, minus PA minus PL, divided by, and now this is the case where in the denominator, because in the null hypothesis I assumed that they were equal, right? The null hypothesis, I assumed that both of the proportions were equal, that PA equals PL, or P placebo, sorry, PL. Since I assume they're equal, then really what I'm going to do is I'm going to treat it as if it's out of 1,000 total people. So my P combined is going to equal the two together. So that would be 15 plus 26, which is 41. So my P combined is 0.041. How that goes into place is then in my denominator for two proportions. And again, use your formula sheet here. It's P hat 1, Q hat 1 over N1. But in this case, it's going to be the P combined. So it's going to be 0.041. That's a 4, trust me. Times point whatever 1 minus 0.041 is 0.959 divided by N1, which is 500, plus, and it ends up being the exact same thing, 0.041, because both are the same sample size. And of course, at this point, I go to my calculator. I grab my calculator and I go stat tests, and I go down to the 2 prop z test, because it's 2 proportions, it's a z test. 15 over 500, 26 over 500. I'm going to test to see that the first one is less than the second one, and then I hit calculate. And I find my z-score is negative 1.75. And let's see, so in my picture, 0z, negative 1.75. And then recall, I'm doing less than, all right, which was my alternative hypothesis. Less than means left end. So this is the area that I shade. And my calculator tells me that my p-value area is 0.0397. All right, 0.0397. All right, so I calculated a test statistic. I found the formula, excuse me, I found the p-value of it. So now I need to make a conclusion. Since 0.0397 is less than 0.05, that was the alpha they gave, I reject the null and accept the alternative. There is sufficient evidence to show that aspirin would reduce the chance of developing colon cancer among all people similar to the volunteers. You know, this is pretty much exactly stated in the question. I'm just restating it as part of my solution. And the reason why I can reject it, don't forget to say this. Some people will just say, I reject the null and accept the alternative. And I'm going to say, well, but why? How do you know? Because my p-value is less than alpha. Since the p-value is less than alpha, then I can move on. All right. That is actually it. That's it for the whole problem. So I finally had myself a good hypothesis test question. It ended up being a 2-prop z test. And in this case, I ended up rejecting the null hypothesis. Just special things to note, and notes here from the scoring guide from the 2015 exam too, that indicated if they said something about simple random sample or anything along those lines, you did not get credit. Couldn't even just say randomness. You would have to say random assignment. Random assignment is what you needed to do. Other notes, the p-value is correct if it is consistent with the alternative stated in the response. So if you happen to find a different p-value and then concluded correctly, you would still get a p. You wouldn't get an e, but you'd still get a p partial credit to go along with the fact that you may have had the wrong z-score. And the conclusion is always related to the alternative hypothesis. All right, that is all, folks, for number 4.